Hello. Okay, so welcome back to the next session. And in this session, we begin with Professor Francesco Pepe, who's going to talk about principles of spectroscopy. So I hope many of you know him, but for those who are not aware, he's the director of Geneva Observatory. And for anybody working in the field of radial velocities and exoplanets would have heard about several spectrographs like HARPS, Espresso. So he's one of the main PIs and design concept experts in this. So he's going to talk to us today about some of these principles of spectroscopy. So over to you, Francesco.
Thank you very much. You can hear me, yes? Today, so I will talk more general about spectroscopy, and tomorrow it will be more about how actually to build a precise spectrovelocimeter. So I put together all this material. Not sure, so don't hesitate to ask, to interrupt me. I said in the beginning, it's good if it's interactive. Don't hesitate. So first question, how would you measure a stellar radial velocity? What technique and what instrument would you use? Okay, what is a radial velocity? Or how do we measure the radial velocity? What is our observable? Sorry? A Doppler shift, yeah? Of what? Of the stellar, okay, the starlight, good. How will this show up, this Doppler shift? We observe at different times, yes, but at what do we look to see the Doppler shift? How can we measure it? Okay, so on the stellar lines. So we need to do spectroscopy of the stellar light. And then we want to see how they change in wavelengths. Okay, so we agree that this is the principle. Now, what instrument do you know, or what would you use to measure these shifts of spectral lines? You would use a spectrograph. Why won't you use a Fourier transform spectrometer? Or why wouldn't you use a Fabry-Perot étalon? You don't have to answer. Okay, but what is coming out, you immediately answer the spectrograph, because this is the reality. We use high-resolution spectrographs to measure radial velocity. And this has a certain historical reason. It is not just by chance that we have chosen that. Here I'm showing a spectrum of espresso, by the way. So such one of these high resolution spectrographs, see this different orders and even different slices for different orders, and you see two fibers illuminate the spectra of two fibers, one illuminated with the calibration source and the other with the stellar light and so on. So my goal of today is just to show how we get actually to this spectrograph. Why did this evolve in this direction? Why do we need high resolution spectrographs? Okay, so that's, you know, these two guys. As Sourav said, there has been different attempts, there are different techniques. The technique that Michel Mayor and Didier Queloz used back in '95 to find 51 Pegasi B was the one of radial velocities, measuring the velocity change. That's the original plot in their Nature paper. Velocity change as a function of time to a certain precision. Here you see that we are not yet at the turtle speed. We are more at about 50 kilometers per hour, or actually even worse precisions. But that was the technique. And to do that, they used a spectrograph. And Sourav also has shown the technique. So we look at the star. When the star is moving towards us, the light will be Doppler shifted towards the blue. So we will have this spectrum here, for example, okay, a whole visible spectrum or near infrared spectrum with many, many spectral lines. Here on the top, you see it as well. Okay, that's a small portion of such a spectrum. Just next to it, I show a calibration source that is projected on the same detector, is our ruler to measure the position. And then when the star moves or changes its velocity, we will see here the velocity. So the stellar absorption lines moving in the wavelengths, which can then be converted into a radial velocity. And just before starting, that's to show where we stand with two very simple examples, that the radial velocity curve, the phase folded for the two planets of Proxima Centauri B. I show these because the scatter and the amplitude is of the order of 20-25 centimeters per second. So it is indeed already possible today to go to the level approaching the signal induced or the radius velocity change induced by our Earth on our sun. So we are not too far away from that. These are short period planets, so it's a little bit easier. If you want to look at a real Earth on 1 year orbit, then you have to guarantee this precision and this ability or this repeatability of the measurement over several years. And that's a little bit more tricky. The other example is that with a spectrograph, we can do many more things. Sourav has shown several examples. Here I'm just showing one of the early transmission spectra made with the HARP spectrograph. So it's a radial velocity spectrograph that you use to do transmission spectroscopy. Because what you need is high fidelity. You need to reproduce the spectrum in the most, or in the way as close as possible to the reality, to the observational reality. So that's another example. So a few input messages here that you should take. Okay, so the extremely precise radial velocities are still important today to find new candidates, especially for the future missions. And they are extremely important in complement to, for example, transit observations to do precise mass measurements for the densities and to start to study the interior. Upfront, radial velocities are done with spectroscopy, and that's the reason why I asked the question. So why can't we go for high resolution spectroscopy on HWO? It's indeed, we are photon starving because we are dispersing the light so much that we are always missing a little bit of photons if we want to go faint. So one other limit is that when doing radial velocities, we are looking at the stellar surface, which is everything but homogeneous and stable and quiet. So we will be impacted, our measurement, our observable will be impacted heavily by the stellar signals or noise. If we are not able to detect them, then it's noise. If you are able to resolve them and model them, then it's signal. And there is a hope for that. But we have to do that. And of course, we have to work in instrumentation, and we are not yet ready to do centimeters per second observations over years. We are not yet there. We are still to work on this instrumental aspect. And eventually, okay, as I have shown with one example, a radio velocity spectrograph is a spectrograph. It's a high resolution spectrograph. The only difference with other spectrograph it is that it has high fidelity. So it's able to reproduce the wavelengths, but also line shapes in a very precise way and very close to the truth. So we have here a lot of potential. And that's our observable. So we are in the optical wavelengths. So we are not able to resolve the electrical field directly because it's too fast, at least not yet, especially when we are looking at astronomical targets, which are photon starving, where the seeing spreads the light over a big field of view, I mean, big arc seconds. So we are here forced to go for intensity measurements, so we can measure the intensity as a function of wavelengths. That's our spectrum. And that's what we want to reproduce in the most accurate way. That's our first approach. Okay? You want now to, if we go back, I want to know the intensity at every single wavelength. So the most immediate approach is that I put a filter in and I observe the intensity which goes through this filter. Oops. Yeah. That's that. Okay. It's very, here I'm reducing the concept to the most, let's say, the fundamental aspects. We have a telescope, which is it's the collecting area. We focus, that's our focal plane. We could actually put the detector here directly in the focal plane, but this would force us to put the filter here somewhere up front, and this would increase the sizes and so on. So we are producing an intermediate focal plane, and then we have a camera lens that refocus our field here, our object, the image of our object onto the detector. And if you want to know the intensity at one given wavelength, we put the filter in. And that's it. What's the major problem with that? Sorry? There are, for sure there will be residuals, for sure there will be biases, but I think we can cope with that. But there is a more fundamental aspect. If I approach my spectroscopy this way, there is just a practical aspect. I have one wavelength at a time. I'm throwing away all other wavelengths, all other intensity. I'm really throwing the photons out of the window. So if I want to do high resolution spectroscopy, I will have such a narrow band, and then I will have to observe every band one after the other. This will take me forever. I can do, of course, a little bit better than that, a little bit better. You have an idea? If I want to use filters, but I not only one at a time, I could do maybe something else. Okay, this will come later, even before that. Yes, even a little bit before. Just two filters instead of one. Okay. Oh, sorry, where is it? Yeah, I forgot this one. Okay. I put a dichroic or even several dichroics. You know what a dichroic is? Okay, it's this here. It's an optical filter that has a cutoff wavelength. So it's transmitting one wavelength that is reflecting the other one, or the other way around. So you put it here. You can have the red here, the blue here, and then I can have two filters simultaneously. And I can reproduce these several times with several dichroics and have several filters at the same time. So at least here, I'm multiplying by 2, 3, 4, 5, 6, 10 my observational efficiency. But you're right, it's still not what we want. It's still not sufficient. I just go back. Okay, that's the filters, by the way. There are different types of filters. These are colored filters. So there is a bulk material that is filtering. They normally are very broad, and I'm showing here them because also to show that the width here is 100 nanometer or something like that. So lambda over delta lambda, lambda over bandwidth is of the order of 10 at most. So the resolving power is very low. And this will force me to do many measurements, one after the other, or with a dichroic, but I will still remain with a very low resolving power. Here I'm showing interference filters, which can be designed to be a little bit more narrow band, and I could do higher resolving power. Do you know this guy? Yeah, you had that? You studied that? Good. It took me years before understanding just two stupid mirrors, how they work and what interference does. Somehow it's really simple, but at the end, when you go into the formula, and there are very strange effects. So you don't. It took me 10 years to understand it. Anyway, so that's a Fabry-Perot étalon. Two mirrors here, okay, which create an interference, and it acts like a very narrow interference filter. It's a very narrow band interference filter. Do you know or do you see what I'm doing here? Okay, I'm collimating the beam to make it parallel before then actually focusing on the detector. What am I doing that? What do I have to do that? Don't be shy. Yes, somehow, yeah. I would have answered in a different way, but I think you understood. Yeah. So if we don't have a parallel, no, we have parallel plates. We want to create interference between these two surfaces. And in order to define the interference for a given wavelength in the best possible way, the beam has to be parallel. Otherwise, if the wavefront is not parallel or plane, then the interference will not occur. Actually, will not occur. There will be multiple interference, and it will become fuzzy, spectrally fuzzy. I will show you what this means exactly in a moment in the formula. Okay, so I have to collimate first, make the beam parallel, go through the interferometer, and then having the detection here. I'm showing here a Fabry-Perot étalon, so two mirrors here with zero Dur or ultra low expansion spacers, which I just installed on the HARPS North spectrograph 2 weeks ago. Sorry, on the HARPS 3 spectrograph on the La Palma Canary Islands. So that's, you can go, it's relatively simply to do the computation, so I will not go into the detail of the computation. You can compute here the interference between the different reflection and beams of the two mirrors, which have normally high reflectance, and the transmission curve, which you get at the end of doing the sum of all these, is that one. So you will get basically no transmission apart from peaks here, which repeat themselves periodically, and we get a transmission peak of almost 100% every time the distance, or 2 times the distance between the two mirrors, is a multiple of the wavelengths. That must be like that in order to have positive interference in between the two waves, the original one, the reflected one, the one which has reflected 2 times, and so on. So if I have this interference condition here, then I get a transmission peak, 100%. Otherwise, it blocks. And you see here also that these peaks can be very narrow, and the higher the reflectance, the narrower the peak. It's called, the width of the peak is called the finesse, or let's say, the higher the finesse, the narrower the peak. Here you have the function, the analytical function, which you see here, which repeats itself, as I said, every time that the phase is a multiple of 2 pi, the phase difference. And this converts into here, this phase, so this converts into that, which is if the incidence angle into the Fabry-Perot is 90 degrees and the index is 1, it converts in this n times lambda is equal twice the spacing. It's exactly the same. And this is just, for the moment, is just used here as a variable or a parameter, f, which stands for finesse. So the finesse, or the reflectance finesse, the nominal finesse, is everything is perfect, is given by the reflectivity of the coding. So that's the finesse. It's the distance here between 2 peaks divided by the width of the lines. And if now I go into the definition of the spectral or the resolving power, should be better, resolving power here, read resolving power, lambda over the width of the line, then I get the order m multiplied by the finesse f. And do we have it here? Yes, sorry. Okay, just I give you here a few numbers. The finesse can be easily of few hundreds, and the order number is the times, the number of times the wavelength fits into the spacing. So if I take a Fabry-Perot with a spacing of 10 millimeter, and I look at visible wavelengths, I will be at order 20,000. Okay, the wavelength fits 20,000 times between the two plates. So I can get here easily very, very high resolving power of several 100,000. However, there is a problem with this filter. Again, a fundamental problem. If I used it exactly in the same way as I did the other ones, okay? I have my telescope, I focus, I put the filter in, I collimate, put the filter in, and then I put the detector. I will have a big problem. Which one? Look at the transmission curve. Sorry? Sorry, I didn't get it. No, if I put this one, I will have periodic peaks. And that's exactly the problem. I don't know which wavelength is transmitted because all these wavelengths, this one, this one, this one, and so on, there will be 20,000 wavelengths which are transmitted. So I have to isolate only one of these peaks. And this can be done with an additional filter. For example, an additional Fabry-Perot at lower order. So I can put here an additional filter, and I would isolate out only one of these peaks. And I will get a very narrow wavelength, very, very high resolving power, and only one. This is for your curiosity, if you want to go into the slides, or if you want to check again how a Fabry-Perot works and what are the limitations. This is the formula you can go through. The problem is that, as I said before, interference happens only if the beam is parallel and the plates are perfectly parallel. If they are not, then the peaks become wider and wider. So the finesse is decreased. And you can write this formula here, 1 over the finesse, the effective finesse squared is the sum of 1 over different components of finesse squared. And the reflectivity finesse, so the natural finesse is one of them, but there is also a defect finesse here, which is basically a measure of the planet, of the quality of the surface. You see, or just look at the non-parallelism here, the parallelism finesse. If the two plates are not parallel, then this L, this gap L between the two mirrors will not be the same here and here. So the transmitted wavelengths will not be the same on the top and on the bottom of the Fabry-Perot. So the peak will transmit over several wavelengths, and the peak, transmission peak, will become broader. So you decrease the resolving power. So there is another effect here, is if the slit is not infinitely small, then you will have here parallel beams going through with different angles, okay, from here or from here, like that. So you have a beam divergence within the parallel plates. And if you look at the distance between the two mirrors, it's not the same if you enter with an angle or if you enter perpendicular. And all these destroys or decreases the finesse. So again, for the records, I will not go through the details here, but the Fabry-Perot has potentially the capability of do very high resolving power measurements, one channel at a time, but you have also to control certain optical parameters in order to get the best possible resolving power. Yeah, that's what you said before. Okay, look at this image here. It's basically what I record here in the back. So after the Fabry-Perot, if I have an extended source, then every place here will produce, so depending on where at the angle which I enter the Fabry-Perot, I will get a different spacing. So depending on the angle here, okay, because you see that if I enter with a given angle, I will be another place on the detector. So I will produce rings here of interference. If I have one wavelength, I will produce an interference pattern, which are rings of interference every time the angle, the distance, or the angular distance is such that the spacing becomes a multiple of the wavelengths. And that's why I see all these rings. But you may have seen that I see two sets of rings. Why? Could have been, but it's not the case. Sorry? See? No, I'm here in a laboratory setup. I have extended source, and I see here rings, but I see two sets of rings. Sorry? Not ghosts. It's not because of the mirrors. I said something, okay. If this is white light, would I see rings? But they will superpose, and they will be white again. I won't see rings if this is a white light source. Yeah, if I'm able to resolve it. But I'm not able to resolve a white light. So I will fully illuminate. So in order to see rings, just to say it the other way around. One wavelength, yeah. So it's a laser, or let's say a monochromatic source. And if I see two sets of rings, there are two lines. Yes, it's a spectrum with two lines, two emission lines, two monochromatic emission lines, who each produces a set of rings. Okay? That's just a test setup. It was a trap to understand whether you understand the Fabry-Perot. No, this is just to show the effect of angle. Okay, what you do normally is you focus on here. Okay, you look on axis and you measure the transmittance here at that position, just for this part here. If you widen up, if you have, for example, a stellar source, then you automatically get, because of seeing, for example, you get an extended slit. So the slit will not be small, it will be big. And if you have white light or a continuum spectrum, then everything will, here it will mix up. So if you take your detector too big, you will actually make a confusion between the wavelengths that you will not be able to do the work anymore. So it's just to show the effect of divergence, beam divergence, and that's it. And in order to show it better, here it's illustrated with two laser lines. Fourier transform spectrometers. Probably you know how they work. Again, I'm just putting the formula here. You have a source. You could imagine that you attach it to a telescope. You have a source. You go into the interferometer. That's a microscale interferometer. You split the beam. That's a beam splitter, 50-50. The beam comes back, it comes back, and it interferes here. And if these two passes are identical, then it will just interfere positively and you will get again the same light. But you can now move this by R. You can move this mirror and this interferogram will change because the path length of the two arms changes. And that will change here. Okay, here I compute the intensity that you measure here. It's the sum of the two components squared, if you want, for the intensity. And so you can compute that, and you end up with an interferogram, which is something that it's in average I0. So the intensity, the integrated intensity of the source, plus a component that oscillates as a function of the wave number, or the wavelength, if you prefer. And the shape of this, okay, I of R, so this interferogram, it's an integral or a sum of cosine. This is the mathematical form of a Fourier transform. So if you want to get the spectrum I of K of the wave number, you just have to invert this. So from the interferogram, you scan the mirror, you record the interferogram, you Fourier transform it, that's why it's called Fourier transform spectrometer, and you get the spectrum. Very good. And here again, potentially, that's the formula for the wavelengths, for the resolution. It's the maximum scan here, the distance you can scan, divided by the wavelengths. And that, if you have a branch that can move by several meters, you can buy Fourier transform spectrograph where you can move up to 9 meters, divided by the wavelengths. It's millions of resolving power. It's a huge resolving power you can obtain with this Fourier transform spectrometer. So what can I do to avoid the Fourier transform spectrometer? I can get the full spectrum by scanning, okay? Now the filters, I can get only one channel time or at a time. So that's here the concept now of a spectrograph, where I try to record as many wavelengths as possible simultaneously. So here again, oops, sorry. Yeah, this one. So telescope, I focus on the slit. Why do I have a slit actually? Why do I put a slit, or why do astronomers put slit? Yeah. Exactly. So you want to be sure that you get only one target in, and not other light from next to the target. So you can define the field of view of your spectrograph. I make it here parallel, and I put a disperser in. A disperser is an element which deviates the different wavelengths with a different angle. Put that in, I focus here, so all the angles, all beams going in the same direction are focused here in the focal plane, and I get here the different wavelengths, one next to the other. I get my spectrum. Now, if I have only one detector and I scan the detector, it's called a monochromator. And if I have several detectors, it's called the spectrograph. Is this okay? Clear? Okay, good. So what defines my spectrum? It's the dispersive element. So the dispersive element is characterized by one parameter here, which is called dispersion. And here I define the angular dispersion. So it's d beta over d lambda. By how much is the beam deviated as a function of wavelengths? Okay. If I have a strong dispersion, d beta over d lambda is large. So I can separate angularly the wavelengths much more than if I have a small number. If I go, that's here, okay? That's the angle here of deviation. If I have here camera lens, then I can define the linear dispersion, which is just the angular dispersion multiplied with the focal length. This tells me at which physical position on the detector each wavelength will be focused. That's what I made before. And okay, that's beta, it's the deviation angle. And of course, for every angle I get here after the camera lens, the beam's focused on a single position. That's X, the position. In an abstract sense, the resolving power, again, lambda over delta lambda, that's the definition. So it's lambda divided by the size, the angular size of a given wavelength beam times the dispersion, or the linear dispersion if I look at the focal plane of the detector. Okay, so it depends. If I have a single line, an unresolved line, it will be projected on the detector and it will have a certain width x. And I can convert x or delta x. I can convert that into resolving power if I know how much this delta x is. That's the formula to convert it into resolving power. Okay, so this was the introduction because I wanted to summarize it a little bit with these two slides, these next two slides. So we can go from simple filters to more sophisticated interference filters like the Fabry-Perot etalon. We can do Fourier transform, and we can do spectrographs. Here, this is of no interest to do high-resolution spectroscopy. Here, that's good. It can go to several 100,000 resolving power. Even better here, Fourier transform. With the spectrograph, you will see why, but I can go to several hundreds to several 100,000. But this will cost me size and money to go there. It's not so easily achievable without investing a lot in instruments. So why did we end up with spectrographs to measure radial velocity? And that's because of that. Have you heard about the Felget advantage? Somebody has heard about that? That's the reason why if you have only one single detector, and it's noisy, then you would go for Fourier transform spectrometer. Because if I compute the signal to noise that I get in a given exposure time, then the multiplexing system here, where I can observe many wavelengths with one single detector, gains above all the others. But this is only true if we are detector noise limited. So if you have read about the Felget advantage, okay, of Fourier transform spectrometer, then remember, this is only applicable if you have a noisy detector. So you are dominated by detector noise. But that's not what we want. We want to have instruments which have low detector noise such that we are limited by shot noise, by photon noise. We want just be limited by photon noise. And if you go to this, to photon noise limit, then they compare like that. If you do a filter, so here I compute the total signal to noise integrated over all spectral beams that you get in a given time t. So if you go for a filter spectrograph or a filter spectrometer, you have in a time t, you will get a certain signal to noise here, which I define as a signal to noise 0, my reference. If you go for a Fourier transform, then you will actually increase the signal because you are observing all the wavelengths with the same detector at the same time. So you will have n channels. So your signal to noise will improve with a square root of n. But since you are observing all the channels with the same detector, the noise is given by the square root of the integrated signal, not only of the channel you are observing. So in that case, okay, you end up by adding a square root of n in the noise component, and you end up with exactly the same signal to noise as for the Fabry-Perot étalon. So there is zero advantage in using a Fourier transform spectrometer with respect to a Fabry-Perot étalon. If you go for a spectrograph and you have n channels, then you will have basically here the same situation as here, but n times. So this costs you n channels. So you need n detectors, n pixels, whatever, but your signal to noise will improve by a square root of n with respect to the two other spectrometers. And that's the reason why we are going, why astronomical spectrograph for high resolution and high precision are all, for the moment, based on that. Okay? Should I wait a little bit more? Do you have questions? Are you confused? Yes, you're confused. Yeah, okay, so the takeaway message is here. I went through these different types of spectrographs or spectrometers because when you are in this business, there are always people who pretend having found a cheaper and better solution. But there is always something that at the end will not work out, and that's basically that at the end. So we are still stuck to, yes, radio loss, to spectrograph. Yeah, but that's the pixels is n. Here. Yeah. There is a T. Yeah. Sorry, that's T. Yeah, that must be T. Thank you. Because I'm looking at each channel. Okay, for any channel, my signal is S. Sorry, that must be T. Okay, so that must be T. So the signal is for every channel is S times T, and the noise is square root of S times T. And I have n channels, so my signal to noise increases by square root of n. Thank you for the typo. Yeah. Sorry. If you are not. Yeah. Yeah, we add up the channels. Yeah. But this is true also for all the others. So here I'm just doing a conceptual comparison, just to compare spectrograph. How to get the best radio velocity out of the spectrum, this is tomorrow, okay? Okay, so I tried to speed up a little bit because I'm extremely slow. Okay, you have already seen that. Remember now, camera, so F, that's the focal length of the camera, the collimator, the telescope here, because here now I'm going through the resolving power. What is the resolving power? And here it becomes tricky. That's my input spectrum. Let's suppose I have two lines here of slightly different wavelengths. I illuminate my slit or my fiber here with these two lines. What does a spectrograph? A spectrograph does nothing else than doing an image of the input slit on the detector. And this for all the wavelengths. And the disperser helps us in separating them spatially. But what you see is an image, is a monochromatic image of the input slit. That's what you see. Okay, so you will see here, if you have a slit, you illuminate your slit with a star, you will filter the slit and you will get an image of the slit here. If your slit is very, very narrow, your image will be more narrow, but not infinitely narrow. You know why? This dispersion, diffraction inside the spectrogram. So here we are limited by diffraction. I had written. Oh, that's so good. And here we are limited by the slit. Exactly. So let's see. Okay, again here I draw that 3 times. So you have the slit. You have an image of the slit, but here it's very narrow, but here the diffraction will make your PSF actually wider than your slit. That's on the detector. Here you collimate, disperse, focus. And if the slit is broader, then you will have a broad image of the slit convolved with your PSF, which can be aberrations, but can also be diffraction. So if your slit is very narrow, you will end up by being diffraction limited. So the divergence inside the collimated beam is given here by this formula. You should all know by heart, okay, where D is the diameter of the collimator. If you are limited by the slit width, then the divergence will be given by the slit divided by, and this is here F collimator, sorry, so the focal length of the collimator. And then this converts on the detector, you have to multiply with the focal length of the camera. So you can go through the maximum resolving power you can get here, lambda over delta lambda, depends on the dispersion and the divergence. Divergence here, in the best case, is given by the diffraction within the spectrograph, because the collimated beam is only 10, 20 centimeters wide. So you will have diffraction, and so you will end up with this formula here. If your slit is broader than that, so if you're dominated by the divergence of the slit here, okay, it's exactly the same formula, but this time the divergence is given by the slit width, the physical slit width divided by the camera focus, then you will end up with this formula here. Okay, so you decrease the resolving power by the ratio between the diffraction and the divergence, given the geometrical divergence defined by this. That's the formula you should remember, which will define the costs of your spectrographs. That's 1-to-1. Okay, you can't do differently than that in a spectrograph. because of the conservation of the étendue or the Lagrange invariant. Okay, when you compress the beam, it becomes faster. You can't do, it's like a fluid, an incompressible fluid. And this leads you to this, that's the formula before. The resolving power increases if you increase the collimated beam. So you have to increase the spectrograph if you want to get a higher resolving power. It decreases if you make a large field of view. A big fiber will result in a lower resolving power. A big telescope will result in a lower resolving power. And the dispersion, of course, helps you if you get a high dispersion. And so the next 10 minutes, I will show you a few examples of disperser, because we want to get the highest possible dispersion here to increase our resolving power. Okay, so this is the formula to remember when you build the spectrograph. There is no miracle around that. Yeah, that's, if you introduce, you might ask yourself, and if the spectrum is sampled with pixels, what happens? Yeah, you just add a new component in the convolution. So there is not only the PSF or the diffraction, you will also have to convolve with your image of the slit. You have to convolve the pixels, the response of the pixel. So you will get something like that. Okay, that's resolved, that's unresolved. But it's exactly the same. Okay, I will not go through this, I think. Just to show you, if I use a prism, I can compute the dispersion that I get with a standard prism of, let's say, reasonable size, 100 millimeter size. I will end up with this kind of dispersion. So 0.03 radian per micrometer. Micrometer is here, is not the distance, it's the wavelength. Okay? Per unit wavelength in micrometer, I get 0.03 radian separation. So if I take two wavelengths which are separated by 1 micron, going through the prism, they will be separated by 0.03 radian. Remember this value. Okay? Grating, a grating spectrograph. If I use a diffraction grating, here I'm not using refraction, I'm using diffraction. Okay, it's a complicated drawing, but it's exactly the same as I had before. So the telescope, a slit, the collimator. Instead of a prism here, I put a reflection grating, camera lens, detector. Exactly the same drawing as before. How does a grating work? That's the grating equation. Every time the optical path of beam 1 and beam 2 and beam 3 are different by a multiple of the wavelengths, I get constructive interference. Now the path length between 1 and 2 and 3 depends on the wavelengths and on beta, on the output angle beta. So my beam is hitting here, this grating. The beams, the different beams are sent theoretically in all directions, but there will be one direction in which they will interfere positively. And this direction is beta, for which the grating equation is honored. Okay? That's the grating constant. So a multiple of the wavelengths is equal to the path difference, optical path difference between the two beams. And you can compute it. It's a little bit of geometry to be done here. it's relatively simple. You can do it yourself. You get this equation here, which is called grating equation, where alpha is the input angle and beta is the output angle. And if you derive this equation, you get with the you end up with the angular dispersion. D beta over d lambda is the order number times the grating constant divided by the cosine of beta. Beta is the output angle. So that's the grating equation. That's the angular dispersion that you get. How much does the angle change as a function of wavelength? It's not zero, okay? There is a dispersion. Why is there a dispersion? Because beta will, the interference will occur only in a given direction beta for a given lambda, for a given lambda. And that's the formula that results from that. So if you look at the output angle beta, you will have again, for one given wavelength, or if you want, you will have several solutions. One given wavelength will interfere at different orders. But that's not very interesting for us. We would like to have all the light going in one given direction, at least for one wavelength. I come back to this on the next slide. In the meantime, look at the number. Okay, I just took here a standard grading you can buy off the shelf, 1,000 grooves per millimeters. If we use it at order 1, so if the path difference between the two stairs in the grading is exactly 1 lambda, for this beta, you get a dispersion of 2 radians per micrometer. Do you remember the other one for the prism? 0.03. So it's 10 times better with a just very simple grading used in first order. It's much more powerful than a prism. Good. So I have these different orders. Okay, one wavelength coming in, and it would interfere here, and here, and here, and here. How does the light know where it should go? Because the interference condition is fulfilled in several directions. So how does the light know in which direction to go? This is called the blaze condition. The blaze condition is if you look here at a single stair, one single element of the grading, if this mirror here acts like an ordinary mirror, then not only the light will interfere if I fulfill the grading equation, but in addition, it will be very efficient in that direction. It will act like a mirror. And so here you see alpha, so I is equal I prime. If this is fulfilled, and if in addition beta fulfills the grading equation, then I am at the blaze condition and I have all the light going in this direction. That's the peak here. So here is my spectrometer or my grating plotted as a function these times of wavelengths, and every time I hit with a given wavelength is a given beta, and then if beta fulfills this equation here, I get here peak transmission. That's called the Blaze condition. If I change a little bit the wavelengths, then beta will be slightly different, and I will not fulfill anymore the Blaze condition, and my efficiency decreases. And what I'm plotting here is order 2, 3, 4, 5, and 6. Okay, they would superpose. And that's my next problem, is how to avoid that here. If I look at a given angle beta, how can I avoid that I do not get 2.5 microns and 1.6 microns and 1.2 microns wavelengths in the same direction? How can I avoid that? Yeah. Okay, cross dispersion, correct? Good. Yeah, just going through, I will be very short. There are different grisms, different gratings types or different dispersers. That's a grism. It's basically a transmission grating. It's the same formula, huh? It's identical. But here I'm making sure that the deviation angle, the average deviation angle is 0 by adding a prism, by gluing the transmission grating on a prism. Because if I had only the grating here like that, then the deviation angle would be like that. So the beam would be deviated in average. And in some spectrometer, you want to avoid that. So you glue a prism in front to ensure that the beam goes straight. There are volume phase holographic gratings, VPH, where instead of having a surface structure, I code a dense, an index variation into a gelatin here, into a material. And these will produce a diffraction pattern identical or very, very similar to the one of a grating. Again, I don't go into the details because the formulas are the same. I want to go first, before explaining why we need cross dispersion, is I want to go to the Eschel grading, which is just a standard grading, but here we push the order to a very, very high level. We want to have high order because the dispersion is proportional to the order. So if we get high order, then we get high dispersion. So I take the grading, and Eschel is in French means stairs, stairways. So that's because it looked like that. And I use it this time in litro condition. And I make this angle here as steep as possible. If I do that, then I maximize the optical path difference between the different beams here. And I get a high order diffraction. And I get this formula here. So it's again the standard grating equation, but this time I maximize the angle beta and the difference in path lengths between the different components here. And that's, for an Eschel grading, that's the diffraction I get if I choose a steep Eschel grading of tangent equal to 4, so 76 degrees. And of course, I didn't choose this by chance, because this is what we use normally in the best spectrographs currently available worldwide. That's typically an R4, a tangent 4 grading with an Eschel grading. I will go tomorrow into that. Okay, yeah. So we are working with the Eschel grading at high orders. We have to separate these orders. We do not want to lose the wavelengths, the other wavelengths. Otherwise, we would just put a filter a box-shaped filter around one order, and we will have a short piece, a short chunk of the spectrum. But we don't want to lose the other wavelengths. So what we do, instead of filtering it, we cross disperse it. So that's the concept, the general concept of most of the radio velocity spectrographs being around right now. You have the entrance slit, which is normally fed by fibers. You collimate the beam. Remember, in order to disperse, I have to make the first the beam parallel. Otherwise, my encoding in angle would be fuzzy. You go on the Eshel grading, you go back, you re-collimate. You do that in order to keep the beam size always controlled. That's called the white pupil mount. It has been invented by famous optical engineer André Baran. It's to make the instruments more compact in diameter, because you have here a huge divergence due to the dispersion. The beam will become bigger and bigger. In order to avoid that it becomes too big, you refocus it and you recollimate it here, and you place the cross disperser at the image of the white pupil. Basically, this is an optical image location of the Eshel grading, where the beam is still white, it's undispersed. That's why it's called white pupil. The beam is undispersed and white, and you re-image this here, and you get a white pupil. And then you focus it, but before focusing it, you disperse in the other directions, and all these chunks of spectra, these different orders, they have different colors. So by putting cross disperser, for example, a prism, a low dispersion prism, you separate all the orders here, and you get an Eshelogram, an Eshel spectrum. That's how it looks like. By the way, here you get a white spectrum because all the orders are superimposed. So you have small chunks of different colors, but they are all superimposed. And you will physically see a white spectrum there. And once you separate, so that's what you would see here, all the orders superimposed. And once you have cross-dispersed them, you will image them on a detector, and you will have different orders going from the blue to the red, all imaged at the same time on the detector, and you will have the full spectrum at high spectral resolution. I think this is a sign that I should stop. That's how it looks like. Sourav has shown that. So these are the different orders, starting from the blue and then going up line by line to the red. And what you see here, these are absorption lines, but it's actually an image of the slit. It's a negative image of the slit, what you see here. Because it's line missing, and as I said before, you are reimaging your slit on the detector at every wavelength. So it's a negative image of the slit. I think I will stop here, but if you want to go through the slides, if you're interested in an example of such a spectrograph, I've shown up the example of UVS. It was a little bit, together with HIRES on Keck, it was a little bit the first of its kind, using big Eshel grading, R4 gradings. So it's a huge instrument. I will not go through that, but if you want, you can yourself have a look. You see one arm of the spectrum imaged on two detectors and different orders from the blue to the red. the separation between the orders, because the cross dispersion is producing a separation that increases with wavelengths if you go with a grating. The prism will do exactly the inverse. And that's the resolution you get if you go for a small slit. If you reduce the slit to 0.3 arc seconds on the sky, and you use the formula I gave you before, this famous formula I said you have to memorize, then you get this dispersion and you get this resolving power with US, provided that you reduce the slit to 0.3 arc second. If you increase it to 1.2 arc second, then you will have all the light in, because the seeing is very good in Chile. It's typically below 1 arc second. So you will have most of the light in. But you will end up, with a resolving power of 30,000. So the resolving power, okay, as soon as you increase the slit, the resolving power decreases because it's inversely proportional due to the formula that I've shown before. I finish with one trick, which personally I never adopted because I think for high precision radial velocity, it's not good if you do it like that. But there is a trick to recover all the light and still have 100,000 or 120,000 resolution in UVS and in other spectrogram. Do you know the trick? You know the trick. You want to have all the light, but not reduce the resolving power. On the same telescope, okay, you just want to increase the slit width, but you don't want to lose light. What do? I told you before that there is the conservation of étendue, so there are no miracles. But there is a trick. No, the same spectrograph, there is a trick how you can increase the slit width without losing the light. You just have to put a small optical component at the right place. Sorry? Increasing the number of grooves. I use the same spectrograph, so I don't change the Eshel grading. I don't change all the other parameters. I just introduce a small component in addition, a slicer. Okay? Suppose that's your slit. UVS has a long slit here. If in the focal plane I introduce such a component that's a prism, two prisms glued one on the top of the other, which actually cuts the image here in 2, 3, 4, 5 parts. So you cut the image and you realign it by this component here along the slit, then you get all the light into the spectrum, into the slit, but you don't increase the slit size. So you're still at the equivalent of 0.3 arc seconds. The light is just redistributed along the slit. Of course, this comes not for free. Okay, this you pay with pixels because you have to use many, many more pixels here along the cross dispersion direction. Okay, that's that formula here. The number of pixels is proportional to the number of slices squared. So you will end up using many more pixels. And you may say now, and that's my concluding word, you may say, I do not care. I have the price to pay the detector, that's fine. That's true, but when you are going faint, and even not too faint, you are adding proportionally to this, you're adding readout noise, because every pixel is contributing with readout noise. You're adding dark noise, and you're adding cosmic hits. So you will have other problems than to solve. I think that's it. Yeah. Tomorrow, I will tell you how now take such a spectrograph and make it to be extremely precise and produce high fidelity spectra. Okay, that will be tomorrow. So I propose to stop here. Thank you. Questions or other questions? Quasi-litro, yeah. So the GRISM, if you go through the numbers, the problem of the GRISM is the resolving power, okay, the dispersion. In HARPS, for example, we use a GRISM as a cross disperser, but not as a main disperser. If you do a GRISM, which it would have to be very steep, okay, so very long. You may also go for immersion grading, which is basically the same, but in reflection, okay? So you can do that, but at the end, you end up with an angle, which is the one of the Eschel grading. So the Eschel grading, since it's in reflection, you double the optical path difference. So the fact of being reflection and in litro will, in addition to the fact that you can have a steep angle, will double the optical path difference. So you will get this beta on the other side, and you will have even a bigger dispersion. Yeah. Yes. That's because of the slit. Okay, so if you fix all the other things, yeah, because the bigger the telescope, you increase the étendue. So if you don't increase your collimated beam, the slit will appear bigger in your spectrograph, and you will have more divergence. Okay, so by increasing the étendue, you make the beam faster. In order to make the slit appear the same size in the spectrograph, you have to increase the focal distance by a factor of 2. If you increase at fixed field of view, so if you increase the focal length of the collimator by a factor of 2, your beam will become twice as big. So that's what you have to do if you want to keep the resolving power. If you take the same spectrograph and you have just a bigger telescope, then your physical size of 1 arc second will be larger. And then you will have it will be larger also in the spectrograph. That's the reason why when people told me, oh, you should take HARPS, which is on a 3.6 meter telescope. Why don't you put it on the VLT? It doesn't work because of the formula that I gave you is you have, that's why the spectrograph is a monster. Okay, if you are seeing limited, the spectrograph will become huge. They grow proportionally with the telescope they have for a fixed resolution. If you go for adaptive optics and you go for diffraction limited spectrographs, then the size of the spectrograph remains constant. Because the bigger the telescope, the smaller the field of view. Okay, because of the diffraction becoming smaller. And the multiplication of the two is constant. So the size of the spectrograph remains constant. Yes, yes, always, always. Yeah, so you've seen, you know how many channels we have in a typical optical spectrograph? Hundreds of thousands. Okay, if you delta lambda, if you take any spectrograph, 100,000 resolving power, you compute delta lambda, lambda by delta lambda, you will compute the number of different channels. If you compute that, you end up with 100,000 to a million. That's the number of channels. You will never be competitive with a Fabry-Perot or with a Fourier transform. There is no chance to compete. But your question is good. How far should we go with an initial spectrograph in resolution? Because as you have seen, the more resolution I have, the bigger the instrument and the more expensive the instrument will be. So how far should I go? And tomorrow I will show you the formula where you actually can decide what's the good resolving power to adopt. But Fabry-Perot and FTS are not competitive. That's so the order length in initial grading is given by the number of grooves I think the chairperson, Priyanka, or whoever should stop whenever. But just here, where is the, here. Okay, so you see that in this formula, by somehow a miracle, the dispersion only depends on lambda, not actually, wait. For a given tangent, it only depends on tangent beta and lambda. So the resolving power will not depend on the groove density here, only on the angle. However, if you make this groove broader, longer, then the order number will go up. And the free spectral range, so the length of the orders, is lambda divided by the order. So if you make your groove density lower, you make your grooves shorter, your orders shorter. and you will have more of them. So you increase the order number, so you increase the number of orders, so the chunks will be shorter, but you will have more of them. And how you decide that? Okay, there is one problem. Not all the groove densities are available on the market, so you have to cope with what you get. But in principle, you can dimension your spectrum to your detector. Okay, if you have a rectangular detector or this way or a square, then you can choose the number of orders or the groove density such to make the spectrum fit best on your detector. It's okay? Yeah. Yeah. I mean, we had once a workshop about heterodyne detection. I mean, and okay, so for the Fabry-Perot, I told for the Fourier transform, I told you what is the limit? It's just the observing efficiency. You cannot do better than that. No, it's not. No, it's because we are multiplexing. It's because we have only one detector. It's just a matter of the amount of detectors. It's not because we are not measuring the electric field, but we could go for measuring the electric field, for example, for heterodyne detection. But again, you have a local oscillator. You have the problem of having the strong intensity difference between the coherent source, the local oscillator, and your astronomical source, which is everything but coherent, spatially and temporally. So you have the beating or the interference will be dominated by the astrophysical source. That's the first aspect. And anyway, you're measuring channel by channel. You are at extremely high resolution, but you're measuring channel by channel. And then you can multiplex it, okay? But still, you gain with respect to a field or a filter spectrograph or a single channel because you can multiplex, and so in a given time you can increase the number of channels. That's you get. But compared to a initial spectrograph or whatever spectrograph where you observe all the wavelengths and you separate them spectrally such that they do not contribute to each other's noise, I think you cannot do better than that. Yeah, in total signal to noisation. Yeah, maybe, yeah. Maybe we should look at a specific case. Yeah. If you have an emission line, individual lines, then you can. Then I'm sure you can. But at absorption spectra, broadband absorption spectra, I'm not sure. You can discuss.